Okay, so these are the notes for functions day 4. So make sure you're in OneNote. You've gone down to functions day 4. And the essential question is, how do you find the inverse of a function? So anytime that you need to, go ahead and pause this, and then you can start it up when you're done writing. Okay, so we have one main idea today, and it's going to be inverse functions. So go ahead and write that in the left-hand column. That's where our main ideas and questions go. All right, so the first thing I want us to look at is a little bit of a geometry and how this relates to inverses. So from geometry, we're going to reflect point A, point B, and point C across this y equals x line here. Okay, so to remind you how we do that, so here's A, and so you're going to measure diagonally. Since y equals x is a diagonal line, when you do the reflection, you're going to measure diagonally. So notice that this is one diagonal away from there. So I go one diagonal here. So there is A prime. Okay. Then I'm going to do C. Now notice C is one diagonal on this side, so then you go one diagonal on the other side, so there's where C prime goes. And then B, if I measure B, B is 1, 2.5, so I go half, 1, 2. So this is a reminder how we do these reflections, okay, across the y equals x line. So if I look at these, so let's write out where the points are, the coordinates, to see what's going on. Because you don't always have to do what I'm doing here, where you're counting diagonally to see where the image point is going to go. So C is at 5, 3. B, the original, so these are all the original points, not the reflected points, is at -2, +3. And then A, the original A, is at 2, 0. Okay, so now let's see what happened to each of these, where the coordinates ended up. So C prime is now at 5. Oops, I did C prime there, didn't I? Let's go back and change that. So C is at 1, 2, 3, 1, 2, 3, 4, 5. C was at 3, 5, and C prime was at 5, 3. There we go. Okay. B prime is now at 1, 2, 3, -2. So B prime is at 3, -2, and A prime was at 0, 2. So what do you notice happened going from C to C prime, B to B prime, and A to A prime? Well, hopefully you see the pattern. Notice that on C to C prime, just the X and Y values change. So what was the X value is now the Y value of C prime. And what was originally the Y value is now the X value of C prime. And that happened for all of these. So whenever we reflect over the Y equals X line, this is what we're doing. We're taking any point, any original point, whatever that happens to be, and when you reflect it over the y equals x line, all you're doing is taking the coordinates and flip-flopping them. So whatever the y value was of the original one is now the first value of this coordinate, which becomes the new x value. And whatever was the x value of the original value goes in the second position, which now makes it the y coordinate of that point. Okay, so if I gave you any other points, let's say I'd given you D and I said D was at 4, -3, well then where would D prime be when you reflect it without actually having to count diagonally? Using this pattern here, what would it be? It should be -3, 4, and that's where it would be. Okay. So keeping this in mind, what you actually found when you plotted A and then you plotted its inverse A prime is you are finding the inverse of that point. The inverse of that point is when you reflect it over the y equals x line. So when they ask us about inverse functions, we're taking that function and reflecting it across the y equals x line. And it goes with this whole idea over here where we take the original point and switch the y and x value around. Okay? So the reason why I was pulling it here is because when we reflect over the y equals x line, you are finding the inverse of that point. Now we're going to be dealing with the functions like we've been dealing this whole chapter, but it's the same thing. I could take 2 or 3 points on that function, reflect it over the y equals x line, which means I just need to switch around the y and x value to get the new coordinate, and then I plot that, and that would be the inverse function. Okay? Now, instead of having to graph it, though, it's nice to be able to just do an equation. So that's what we're going to work on, is doing the equation side, and we'll do a couple of the plotting things as well. Okay, so how to find the inverse of a function. This is already on your notes. First, we're going to switch the x and y variables. Okay, because that's what we do here. We switch around the y and the x variables. Okay, so that's step one. Then we're going to take this equation and solve the equation for y, which means get y by itself. You isolate y, so it's y equals. Okay? And then this new equation is the inverse function denoted by, and then we put this f with the -1 exponent, although we don't say f -1x, we say the inverse function of f. That's how you would read that. Okay, so let's put this into action. So let's do example 1. Find the inverse of the function. So we're going to follow these steps. Now, first of all, what kind of function is part A? Right, part A is linear. It's in the y equals mx plus b form. All right, so then we're first going to switch around the x and y values. So instead of saying y equals 3x minus 5, this is now going to say x equals 3y minus 5. Okay, so that's that switching around the x and y variables. Now we're going to solve this equation and get y by itself. So if I'm going to solve this equation, what do I do first? Right, we got to get y by itself, so you get rid of this first. So I'm going to add 5 to both sides. So x plus 5 equals 3y. So that's gone now. Now what? Divide by 3. All right, so you can either write your equation as, and I'm going to put y just on the left side. You can leave it on the right side if you want. So that's going to be y equals x plus 5 all over 3. Or let's write this so we could actually plot it using slope-intercept form. So then that means we have to divide this 3 into both the x and the 5. So what that gives us, remember, would be 1/3 x plus 5/3. So I would take either one, or if this was the EOC, they would only put one of those on there. So if you're used to writing it as the y equals x plus 5 over 3, EOC might divide 3 into both of those pieces separately and get the second equation here, y equals 1/3 x plus 5/3. So you have to be able to go to the second equation if that's how all the choices look. But when I ask you, like on a quiz or a test, I'll take either one. You don't have to write both, just pick one. Okay? Now let's look at part B. What kind of function is part B? It's a quadratic because you have the x squared as your highest exponent. Okay, so that's your quadratic. So then we switch the x and y variables. So now this is going to say x equals y squared plus 2. Okay, what do we do first? We want to get y squared by itself. We need to get rid of this 2 first, so we do the opposite or its inverse operation. So that's gone. So then we get x minus 2 equals y squared. Okay, now how do I get rid of this squared here? Right, we've got to square root both sides. Okay, now remember when you square root both sides, you get a positive negative. Okay, that was back from Algebra 1, and in Algebra 2a you did that as well. Okay. All right, so then I'm going to rewrite this. So this is going to be y equals plus minus radical x minus 2. Now we can't just leave this equation with a plus minus in it. Okay, so what this means is that you've got 2 options for your inverse. Okay, so we could either write it as y equals positive radical x minus 2, or the function is going to be y equals negative square root of x minus 2. You're going to write both of those down. Whoops. You need to write both of those down as your answer. But each of these by themselves are functions, because if I were to graph this y equals plus minus radical x minus 2, I would get a sideways u. And this sideways u does not pass the vertical line test to say it's a function. Okay, but the square root of x minus 2 is going to be half of this parabola. It could be this half. That could be the part that's the positive x minus 2. And then this other part in green here could be the negative square root of x minus 2. Okay, so when you put them together, yes, it's a parabola, because remember the original equation was y equals x squared plus 2, which is a parabola facing upwards, a U shape facing upwards. And if we reflect it over the y equals x line, which is what you're doing when you find the inverse, then it's going to be a sideways parabola. Okay, so then that doesn't, together, if you just left it as y equals positive negative square root of x minus 2, you would get that wrong, because that is not a function. Okay, and in this case, when you have to split it up, we're not going to use this f negative 1 of x, this inverse here, we're not going to use that. You're just going to leave it as y equals. Okay, so down here on my answer, we don't know which of these, unless you actually graph it, which would be the top part and which would be the bottom part of this sideways parabola. But we have to write them as 2 separate. You can't have them together. It's either this, y equals the square root of x minus 2 is the inverse, depending on any restrictions. And in college algebra, you'll learn more about those restrictions. Here, we're just introducing this idea of inverse. And then, or the answer is y equals the negative square root of x minus 2. Okay, depending on the restrictions. Now, we're not going to go into those restrictions, but know that there are restrictions that you'll learn in a later math class in college algebra. Okay, so if you got the plus minus because you had to square root both sides of an equation, that means you've got 2 possible inverses. The y equals radical x minus 2 or y equals negative radical x minus 2 because of the plus minus in front of the radical. And actually, I need to go back and change some notation here. So these I actually should have put, instead of y equals, we need to put the f inverse part. So the f negative 1 of x, f negative 1x, that's the inverse. This one has an or because it's the same thing. It's not a plus minus situation. It's just changing the way it looks on part A. So the or on the answer in part A is not that there's a sideways parabola or anything. This is still a line. 1/3 x plus 5/3 is still a line, and so it's still a function no matter which choice you write. It's just a matter of preference, the way you want to write it on part A. Part B, since there is a positive negative sign when you square root both sides, then you're going to leave it as y equals, we're not going to put f inverse of x with the f negative 1 of x, because we don't know what the original, we don't know which one of those, if it would be the top part or the bottom part that we're worried about. Okay, so we're just doing the surface level here. We're noticing if it's plus minus, it is two separate equations. It's one or the other. Okay. All right, example 2. If they ask you to verify that these two functions are inverse functions of each other, okay, so they're inverses of each other, you're first going to do the composition of the two. Okay, and we talked about compositions on day 3. So basically what I'm going to do is f the composition with f and inverse of x, f of x. Okay, so that means you take, remember we put f, and then I'm going to put in the inverse function here, which is 1/4 x minus 1/2. Okay, so first do the f inverse of x composition. Okay, so now we're going to do that. So if I were to plug in 1/4 x minus 1/2 into f, we would get 4 parentheses 1/4 x minus 1/2 plus 2. So remember, you're taking this inverse, which is 1/4 x minus 1/2, and then going to the f function. Going to this f function, and where I see the x is where I plug in the 1/4 x minus 1/2. Okay, so do that composition, and if when you simplify, you end up with only x, they are inverses of each other. Okay. All right, so let's go ahead and simplify and see what we get. Okay, so we're going to distribute this. So what's 4 times 1/4 x? That's going to be 1x, or x. And then 4 times negative 1/2 is negative 2. And then plus 2 at the end, which negative 2 and 2 cancel, so you are left with x. So these are inverses of each other, and here's your proof. Okay, so when they ask you to verify if two functions are inverses of each other, you do the composition, so plug one into the other, and it doesn't matter. I could have actually plugged in the f of x into the inverse, and again, it doesn't matter which composition you do of the two. And as long as you come up with just x in the end, everything cancels, is out of there except for the x, then you would say they are inverses of each other. Okay, that's how you verify that. Now you could do the work, like take an f of x and do the work to show what its inverse is. That works too, to show that, once you do the inverse of f of x, you end up with the 1/4 x minus 2, so showing all of that work, that would have worked out too. That would have been proof. Okay. All right. All right, and now we're going to find the inverse, graph the inverse, and decide if the inverse is a function. Okay, so then part A, we have 2x plus 1, And remember, f of x means it's like your y variable. So you're going to first switch your x and y. So now we're going to have x equals y plus 1. Okay. Now what? Minus 1. So x minus 1 equals 2y. We've got to get rid of this 2. Now I'm actually going to divide it into everything because it'll be easier to graph this if it's in y equals mx plus b form. So then I would get y equals 1/2 x minus 1/2. So this is our inverse. And I'm not going to put the f inverse stuff yet until I know it's actually an inverse, or until I actually know it's a function. See if it passes the function test, okay? So negative 1/2 is my b. So that would be in between these two here. And then we go, slope says 1/2, so we go up 1 to the right 2. So I'm right here. So when you go up 1, you're actually in between 0 and 1 up here. And then you go over to the right 2. And so here's my inverse. And sketch that in. Really, you just need the 2 points to be able to sketch that in. Okay. All right, so that's the sketching part. Or graph the inverse. So we found the inverse here. We graphed the inverse. Now we have to decide if it's a function. And remember, once you see the graph, how do we decide if it's a function? What do we use? All right, we use the vertical line test. So if I drew a bunch of vertical lines, it would hit each time it would only hit in one spot. So then that means that this is a function. So now that I know the inverse is a function, then I'm going to go back and change it so that this is the notation f of inverse, the inverse of f of x with the -1 piece, like that. Okay. If it's not a function, then we would just leave it as y equals, like we did on that or problem over here, where we left it as y equals this or y equals this. So we didn't actually use the inverse function because these together, notice it was a sideways parabola, so this would not pass the vertical line test. Okay? All right, I want you in your table to try part B. Go ahead and pause this, and you in your table try part B. Find the inverse, graph the inverse, and decide if the inverse is a function. All right, so you should have switched x and y, so this would now say x equals y squared minus 1. Then we would have, you should have added 1. So x plus 1 equals y squared. Then square root, which means we're going to have a plus minus situation. So y equals plus minus radical x plus 1 is what you have. But remember, then that means we've got two possible answers. Y equals positive radical x plus 1, or y equals negative radical x plus 1. Okay. Now, I already know with this plus minus situation that we're going to have a sideways problem when I graph them together. Okay, so that means it's not going to be a function, so already I'm going to leave my y's there. We're not going to put the f -1 stuff. Okay. All right, so we found the inverse. Now we're going to graph each piece, and I'm actually going to color code this so that you can see the part on the graph. So I'm going to change this function to green here, so that when we graph it, we can see the differences. So you may want to change it as well. Okay. All right, so I'm going to do the blue one first. So let's just make a quick little table. So these square root ones work the same as all of the others. So since this +1 is under the square root, it's very similar. Remember, if I were to have x plus 1 in parentheses squared, when we're doing all that shifting stuff, what did this x plus 1 in parentheses squared mean? It means we shift it 1 to the left. It's always opposite of what you think it is when it's in the square root or in the absolute value, or I'm sorry, in the parentheses, the absolute value, or even the square root works the same way. Okay, so whatever's under the square root, you're shifting right or left, and it's always opposite of what it thinks, what it looks like. Okay, and that's always going to be true with all of these. We've been talking about all of these shifts are the same. It's just there's a radical, or there's an absolute value instead, or parentheses instead, but whatever's inside the parentheses absolute value or the radical in this case goes right or left. And then whatever's outside past those signs is up or down, and it keeps the sign. Okay, and then if there's a number in front, then it can make it steeper or wider. Okay, so that means that this is going to be at 0. Nope, sorry. -1. And then there's nothing after the radical. So that means its vertex is at -1, 0, because it's opposite of what's under the radical, is your x. And then there's nothing after the radical, so then that's your 0. Okay, so now let's pick two numbers on each side of this x value. So -1, one number smaller is -2, and a number bigger than -1 is 0. So remember, we try to pick 2 points on each side of that vertex. Well, if I plug in -2 here, if I do the work, so I do -2 plus 1, what do I get under the square root? We get a -1. Can you take the square root of a -1? No, you would get an imaginary number like you talked about in Algebra 2a, which we can't graph an imaginary number. So then this, I'm just going to put in, no, I don't want to put an X. I'm going to put UND for undefined. So this is a spot where it's undefined, so I'm not going to have anything on the graph for this point. So I can't graph -2 on the X. Okay, let's plug in 0. So again, I'm doing this blue one here. So 0 plus 1 is 1, and the square root of 1 is 1. So I at least have 2 points to graph here. So I've got -1, 0, and then we have 0, 1. So that blue graph is going to be a curve like that. And remember, this is a parabola on its side, so that makes sense. It's half of a U shape. Okay? All right, now let's do the green. So the green, notice again, it's going to be -1, and there's no number after the radical, so it has the same vertex. And that will always happen with these plus minus ones. They'll have that same vertex. So I'll pick one number smaller, -2, and then I'll pick one number bigger, 0. Okay? So if I did negative radical -2 plus 1, I still end up with the same issue. -2 plus 1 is -1. Can't have a negative under the radical, so this is undefined still. Now I'm going to do negative square root of 0 plus 1. So 0 plus 1 is 1. The square root of 1 is 1, but there's a negative sign in front, so this one's going to be at 0, -1. Now if I plot the green graph, remember I'm not going to be at -2 at all, so it starts at this point. Then I go 0, -1 is the other point. So that is that shape, which, like I said, when you have this plus minus situation, when you do the inverse and you have a plus minus, it's a sideways parabola. Okay. Now, deciding if it's a function or not. Together, with the blue and the green graph together, it is not a function. But if you were just to graph the blue, would it be a function? If I ignored this green and I just looked at the blue, would that be a function? Yes, the blue by itself is a function because it would pass the vertical line test. Same is true with green. If you didn't have the blue one on the graph and you just graphed the green one, that would pass the vertical line test. But together, these are not, does not make a function. So let's make that note. So together, different color. Together, they are not a function because it's going to fail the vertical line test. Okay, so when you graph these two together and they're on the same graph together, then they're not a function. But if you graph each separately, each on their own graph, then they are function. Each is a function. So together, like I have it on my graph, if I put them on the same graph together, then they are not a function because they fail the vertical line test. This is the inverse. If I graph the blue on its own graph and the green on its own graph, those separately, each of them separately is a function because they would pass the vertical line test if they were both on their own graphs. Now, when you get to a later math class in college algebra, then you would have to be more specific because they would put restrictions on the function. Okay, I just wanted, this is your opening to that, and then those of you going on to college algebra, you'll go a little further than this even. Okay. All right, so right-hand student, explain to the left-hand student what you're finding graphically when you're finding the inverse of a function. So hint, this was something we talked about at the beginning of the notes today. So what are you finding on the graph when you're actually finding the inverse of a function? Go. Okay, so hopefully you said something like when, maybe if I can get this right, there we go. When finding the inverse, you are finding the points of the graph reflected over the y equals x line. So remember at the very beginning when we took those points and reflected them over the y equals x line, and notice it was just switching the x and y variables around to plot that point, that you were finding the inverse of each of those points. So when we do that for a function, when we reflect that function over y equals x, that gives us the inverse function. Okay, so that's going to be very helpful on some problems. If you remember what you're finding graphically when you're doing the inverse function algebraically, you're not even graphing it, you're just trying to find the inverse algebraically. What you're finding is if you were to take all of the points that are on that function and reflected them over the y equals x line, then that would give you the resulting inverse function. Okay. All right. So I want you to find the inverse of the relation. So this line, y equals 1/3 x plus 6. So go ahead and do that. See if you can do that in 2 minutes or less. So pause for 2 minutes and get that done, and then we'll go over it. All right. So work-wise, you should have had this. Then we subtract 6, so you should have had this step. Now to get rid of this, you're multiplying by the reciprocal of 1/3, which is 3. You got to distribute it to both. So you should get, for your inverse, actually let's use the inverse notation because this is a function. Because every line will be a function except for a vertical line, because then it wouldn't pass the vertical line test. So we would have 3x minus 18 is what you should have got. And since it's a line, it is a function, and so that's why I'm using this function inverse notation. Okay, your assignment is the Functions Day 4 worksheet, so do that practice. The answers are on Schoology, so whatever time is left, you should be working on that and checking your answers to make sure that you're doing it correctly. And then you will have a quiz over this tomorrow.